Hello, this is a video tutorial for amplitude modulation and demodulation experiment. The aim of this video is to discuss about the very basics of it and things to expect when you set out to do it in a lab. My name is Vaibhav. First things first, we need to understand what is modulation. The literal meaning of the term modulation is to alter, to change. To modulate something means to change it. It is the process of altering one or more properties of a periodic waveform such as amplitude, frequency, or phase in order to convey or transmit information. More precisely, a low-frequency signal like human voice is used to change one or more properties of a high-frequency wave using some complicated circuitry. We call this process of alteration modulation. The high-frequency wave is called the carrier, as it carries the low-frequency signal across. The low-frequency signal is called the modulation signal or the message signal. Since we can alter multiple properties of a carrier wave as per the needs, there are various types of modulation techniques possible. These methods are named after the properties of the carrier wave that are altered. The methods are broadly divided into two types: continuous wave modulation and pulse modulation. These methods can be further classified, but we'll focus only on amplitude modulation in this video. Before we begin understanding the technicalities of the process, we'll see an intuitive way to think about modulation. Imagine we have a task, which is to simply throw a piece of paper to a spot, say 100 meters away. We're not allowed to walk to the place. How can we do it? The first way we could think of is to simply roll the paper up like a ball, a crumpled paper ball, and try throwing it. It'll probably fall down in a few meters. We can also try folding the paper into a nice little plane and send it a fly. We've increased our chances of success, but still not 100%. Chances are our plane will crash within a few meters, or the wind might change its course forever. Is there something better left to do? Turns out there is. We can take our paper, wrap it over a piece of rock or pebble nice and tight, and then throw it. Our intuition tells that this method is much more effective for the task at hand. You may be thinking, what's the analogy? The reason why paper alone couldn't be thrown 100 meters is simple. It's very lightweight. Air resistance and gravity are enough to ensure its fall within a few seconds. When we wrap paper around a rock, we're adding weight to the paper. The assembly of rock and paper is much more effective in combating air resistance and gravity. This is the basic idea behind modulation. The paper can be thought of as a low-frequency message signal, while the rock as the high-frequency carrier signal. Going by the same logic, the plan to send a low-frequency message signal to long distances involves wrapping it over a high-frequency carrier wave. This wrapping modulates the carrier in a specific way that can be coded into a meaningful message across ends. A high frequency means more energy, and a wave with a high frequency kind of looks like this, whereas one with a low frequency might look like this. And this is what the modulated wave is supposed to look like. But why should we even bother about modulation? We already know from electromagnetism that an antenna capable of producing electromagnetic waves of wavelength lambda needs to be about a quarter length in lambda. A low frequency means an extremely high wavelength, which means longer antennas, which isn't very practicable. Another reason for modulating the message is that most of the communication done via electromagnetic waves takes place in the atmosphere, which is a complex medium. That is to say, it has a variety of molecules, both living and non-living, which impact and limit the efficiency with which electromagnetic wave propagation can be established. Third is multiplexing. We do not want to set up a transmitter-receiver combination for each and every user. An example of multiplexing is that in a radio station, waves are transmitted using a few antennas placed strategically around the city, but almost every household has a radio set. It can be tuned to a particular frequency in order to receive the broadcast. We take a moment to look at the mathematics behind amplitude modulation. It is possible to write the modulating signal as this. The subscript m stands for the message signal, where all the modulation frequency components f sub m are all within some information bandwidth, which extend from about 0 Hz up to a maximum frequency f max. The summation in the equation is over the variable subscript m, where m runs from 1 to n. The carrier can be written as this. F sub c is the frequency of the carrier. These two equations together generate an amplitude modulated wave S of t that can be written like this. We can notice that this wave has a frequency equal to that of the carrier, while its amplitude is being varied according to the message signal m of t. This last expression on further mathematical manipulation reduces to a more informative form, which is this. This tells us that S of t, the amplitude modulated wave, is actually composed of three parts. These are the carrier, which is unaffected by modulation, the upper sideband components Fc plus Fm in the subscript, which are an upconverted copy of the original modulation spectrum, and the lower sideband components Fc minus Fm in the subscript, which are a mirror image of the upper sideband spectrum. This graphic shows what the equation is actually trying to say. The message signal were all in the information bandwidth on the left. The process of modulation has created a band around the carrier frequency, f sub c, on the right. This page shows the circuit design of a very simple amplitude modulator. The modulator circuit consists of two NPN transistors and some resistances. On the top left, we see a DC source connected to ensure proper bias of the transistors. Next is the carrier signal, which is a simple sinusoid of a very high frequency, 10 to the 6 Hz. Below it is the message signal that is to be transmitted, which is also a sinusoid but with a relatively low frequency of 1000 Hz. The entire circuitry within the blue dotted lines are packed into a little box, and we call this box a modulator, more specifically an amplitude modulator. This box is fed with a high frequency carrier wave, which looks like this, and a low frequency message signal, which looks like this. The modulator combines the two and produces a wave that looks like this. We call this packety wave an amplitude modulated wave. A closer look reveals some interesting features about it. The amplitude modulated wave has two components. A high frequency component of the carrier signal, amplitude of which resembles a message signal. The message signal seems to have enveloped the carrier according to its instantaneous amplitude. We've truly made some efforts and sent a message across, but it has been coded into an amplitude modulated waveform. The next thing to do would be to decode it. This is what demodulation precisely is. It is the inverse process of modulation. It also goes by the name of detection. It is the process of recreating original modulating frequencies or the message signal that was used to modulate the high frequency carrier wave during the process of modulation. The rock and paper analogy works just fine here as well. Demodulating means we're going to separate the rock and the paper, since all we ever wanted was the message. The carrier has done its job. The amplitude modulated wave is now fed into a box. We call it an amplitude demodulator. This box has some circuitry in it, which is basically a filter circuit designed to get rid of the high frequency components. This is the stuff inside the demodulator: a diode D, capacitor C, and a resistor R. The amplitude modulated wave is fed from the left, and we obtain the original message signal on the right. When the amplitude modulated wave enters this circuit, the diode chops off the negative halves of it, producing an output like this. The resistor and the capacitor in the circuit are chosen such that the rise and fall of the voltage across the capacitor obeys the message signal. More accurately, the inverse of the product, RC, needs to be around the frequency of the message signal for a faithful replication of it. When these conditions are met, we obtain a message signal. We finally turn our heads to some challenges that amplitude modulation poses. First is that it renders a lot of transmission band space useless. The amplitude modulated wave essentially carries two copies of the modulation pattern, one in each transmission sideband. As a result, it occupies a transmission bandwidth that is twice as large as that of the original information. The number of independent transmissions we can make will be limited by the range of frequencies available and how much bandwidth each transmission requires. Second, amplitude modulation is vulnerable to interference with other electromagnetic pulse sources like power drills and radars. This is the reason why we hear buzzing, crackling, and whistling noises while operating an AM radio. Third is that even in the case of the largest acceptable amount of modulation, only one-third of the total transmitted power appears in the modulation sideband components of the amplitude modulated wave. Put another way, this means that at least two-thirds of the transmitted power is devoted to sending a steady carrier wave. This power is virtually wasted. It only serves two purposes: to let the envelope detectors work correctly and to provide a steady signal which is maintained when there is no actual modulations, simply confirming the existence of the transmitter. Fourth on the list is the inability of the demodulator to exactly replicate the message waveform. This is because the circuit relies on the behavior of a diode, which allows current through when the input is positive with respect to the capacitor voltage, and stopping of the capacitor voltage to the peak level by blocking any current from flowing back through the diode when the input voltage is below the capacitor voltage. Unfortunately, all real diodes are nonlinear. The current they pass varies with the applied voltage. As a result, the demodulated output is slightly distorted in a way which depends upon the diode's IV characteristics. The circuit also suffers from the problems known as ripple and negative peak clipping. These effects are shown on this page. The ripple effect happens because the capacitor will be discharged by a small amount in between successive peaks of the input AM wave. Lastly, we're faced with the issue of overmodulation. To see why, let's consider what happens when the carrier is modulated by a single sine wave, and it looks like this, where m of t is the message signal. If a sub m is greater than 1, this means at times 1 plus m of t is less than 0, and the carrier becomes phase inverted. The process is shown. An envelope detector can't know that the carrier phase has been altered, hence it just responds to the positive peaks of the inverted modulated carrier. This means it produces a distorted output whenever the inequality 1 plus m of t less than 0 is satisfied. A number of more complex and expensive techniques can be used to avoid this problem.
That's enough for the information we needed. Let's try out what we've learned already using a computer simulation software. We'll use LT-SPICE. It's basically an analog circuit simulator. It's a freeware, meaning you can simply download and start using it without paying a penny. This is the LT-SPICE environment. It's fairly straightforward. We'll add two components: voltage sources. We'll ground them at proper ends. Pardon me. And one of these will be a message signal. I'll make this one a message signal. I'll make this a sinusoid with an amplitude of 1 volt and a frequency of 1000 Hz. Let's make this a carrier signal. Again, a sinusoid, amplitude 1 volt and the frequency 100k. That's about it. We run the simulation. We want the simulation to go on for about 0.01 seconds. This screen right here will show the output. If I take the tester at this point, I get the message signal. At this point, we should expect a very high frequency carrier wave. And indeed, we get one. Now, in order to see the modulated wave, we should just add a trace right here. We'll include the two voltage sources and we'll simply multiply the two together, because this is basically what the amplitude modulator is doing. And we have our amplitude modulated wave. Let's see on the big screen. Here it is. This is the amplitude modulated wave that we obtained. We need to keep in mind that since we're doing it on a computer, we obviously aren't taking into account any dissipations that would be present in reality. What you'll observe on the CRO will be a bit different than this. Another interesting thing that we can do is to check if this wave really carries the various sidebands along with the baseband signal frequencies that we talked about. For that, we'll simply tell the computer to do the fast Fourier transform of this wave, or the FFT.
I'll change the scale on the left into a linear one. This is a much more informative picture. As claimed, the modulation has produced a band instead of just one frequency. We can see a band around the 1K mark. Let's check if we have the sidebands around the carrier as well. We'll zoom. We do. We can see that the carrier signal was peaked at 100K, but we can see a range of frequencies around 100K. This is the range of frequencies around 100K. Therefore, we verify that indeed modulation introduces sidebands and generates an array of different frequencies. Amplitude modulation was the earliest modulation method devised for transmitting audio in radio broadcasting and came into being around the year 1906. Since then, the technology has improved significantly. There is an advanced version of amplitude modulation that you might be interested in. Some transmission systems adopt a modified form of amplitude modulation called the single sideband modulation. This is essentially an AM wave with one sideband suppressed or filtered before transmission. SSB modulated transmissions are called either upper sideband, USB in short, or lower sideband, LSB, if you're in a hurry, depending on which sideband is used to carry the modulation information. By using the SSB modulation, we can double the number of transmissions which will fit into a given transmission band. However, SSB transmitters and receivers are much more complicated and expensive than the simple AM circuits described earlier. As a result, they tend only to be used for specialized purposes like aircraft or naval communications. We'll end the video with a small discussion on an amplitude modulation performance factor, followed by a quick revision. We're interested in knowing how good or bad the modulation is. An important parameter of an amplitude modulated wave in this regard is the index of modulation, also called the depth of modulation, which measures how strongly we've modulated the message signal. It is defined as the ratio of the amplitude of the modulation signal to the amplitude of the carrier signal. It is usually denoted by the Greek alphabet mu or the uppercase M. Multiplication by 100 gives us the percentage modulation. This is an example of an undermodulated wave for which the index of modulation is 0.5 or 50%. Second in line is what we call a perfectly modulated wave with an index of 1. The last one we've seen already and is termed an over-modulated wave. Its index of modulation exceeds 1. An amplitude modulated wave like this is bound to cause distortions in the output. Let's do a quick recap of the important points to take home from this tutorial. You should keep in mind that it is possible to communicate information by modulating a carrier wave. Amplitude modulation uses variations in the carrier size to convey information. These amplitude modulations can be demodulated using an envelope detector. We've also seen that this form of detector suffers from ripple and negative peak clipping distortions. The fact that the magnitude of the modulation must be limited to avoid distortions arising due to the carrier phase inversion. That single sideband and suppressed carrier methods exist and are less wasteful of transmission bandwidth and power. The drawbacks of these improved forms of AM is that the receiver or the demodulator becomes more complicated, expensive, and difficult to use. Lastly, the fact that the amplitude modulation is wasteful of transmission bandwidth and transmitter power and is sensitive to interference. The following resources were referred to while making this tutorial video. That's all folks. Thanks for watching.